Section 5.1, Introduction to Normal Distributions and Standard Distributions. Normal distribution, as talked about before, is basically the bell curve we see. It's also called the normal curve. Now, we were talking about mean, medians, and modes. What I want you to keep in mind is when you have a normal distribution, the mean, which is the middle, the median is the middle, the mean, which is the average, and the mode are all equal to each other. It is a bell-shaped curve, hence called the bell curve. And symmetric are not mean, going down the middle. Man, you flip it over itself. And the area under this is 100%. We talked about standard deviations before, and I'm going to go through this in a little bit to explain how we arrive at this distribution. Now, suppose I have some data here, and what I have here are, we go to the campus, and I want a survey of the color of the cars on campus. On the left, I have graph by raw data, 23 red cars, 65 blue cars, 42 yellow cars, 19 black cars, and 73 white cars. When I add all those up, that's 222. If I divide the color of each car by the total number of cars, for example, red cars at 23 divided by 222 is 10.36%. And I want you to look at something here. On the left is raw data, on the right is percentages, but it's the same shape because the proportionality is the same to each other. Now, in a probability density function, when we set up this histogram, which we learned in Unit 1, again, the total area under the curve is equal to 100%. And as we said before, it can never be negative. Now, what I have here on the left is the age someone is first diagnosed with Parkinson's disease. And this is raw data. And a way to read this is go from left to right. I'm not going to read all the data here, but from age 10 to less than 15, there's 4 out of 1,000 diagnosed. From 15 to less than 20, there's 13 out of 1,000. 20 less than 25 is 14 out of 1,000. And so on and so forth, all the way up to age 100. Now, as I said before, if I just do the percentages, you see the same shape. Because the same proportionality to each other. When I put those proportions, this adds up to 100%. And you can see towards the middle, from age 50 to 55, I have 12%, 55 to less than 60, 11%, 12%, 60 to less than 65, and then from 65 to 70, less than 14%. It's most concentrated down the middle. Now, when we looked at the possibilities, remember our data before with number of successes who chose Facebook. We had our percentages here, 0 successes, which is 0.0011, which is 0.11%, all the way to 6 successes. We did a calculation here with the binomial formula. And I want you to notice something here. It doesn't matter the combinations, the total summary. In other words, I could have 3 successes. It could have been out of 6 people. The first, second, and third, the second, third, and fourth, fifth, and sixth. First, third, and fifth, second, fourth, sixth. There's many combinations. But when we sum up how many, regardless of combination, successes there are, the greatest number are, in this case, 4 successes, 32%. The second greatest number is 5 successes, 27.92%. And then the third greatest is 20.62. And as you can see, it's kind of more towards the middle and gets diminishingly smaller on each end at 0 success and 6 successes. We also talked about the coins. We had 3 pennies. There may be multiple combinations to flip these. We have heads, tails. But what we're looking at here doesn't matter which combination. What is the possible outcomes in total? And we had this graph here. And again, you can see while there is different combinations to get 1 head or different combinations of 2 heads, It's contrary towards the middle. It doesn't matter what combination. We want to know the total summary of when we get one head or two heads. And again, even on here, you start seeing the bell curve. More concentrated in the middle, diminishing on both ends. And you can see this, the more data you have and the more combinations there are, the greater the bell curve where it starts showing a normal distribution. And this is where we arrive at this. Now, I could flip 21 different coins. Now, what are the possibilities? The first coin only getting heads, and there's only one. What's the possibility? Or I'm sorry, there's 21 possibilities. Possibility of getting no one getting heads. Number combination is only one. It means all 21 pennies got tails. What's the possibility of 21 pennies getting one head? It's 21. Why? Because I got 21 pennies. The first one would be the head, or the second one would be the head, or the third one would be the head, or the fourth one. So there's 21 possibilities. It starts getting a little hairier the more we look at it. What's possibly getting two heads? Well, it could be the first head and the second head, first head and third head, first head and fourth head, first head and fifth head, all the way to 21, or the second head and third head, second head, fourth head. And you can see there's 210 possibilities. And the larger we go with the success of getting heads, you can see the greater it is. In fact, at getting 10 out of 21 heads or 11 out of 21 heads, there's 352,716 combinations here. And when I do those percentages as before, one out of there's by the way there are 2,097,152 combinations total, and you can see what's the percentage of one out of 2,097,152. It's practically zero. If I go to getting 11 heads, doesn't matter what combination of the 21 pennies, 352,716 divided by 2,197,152, it's 16.82%. And I've graphed it here, and I've basically rounded it up so it'd be easier to read. And you can see we have 2,097,152 combinations. But you can see the greatest number of combinations are concentrated where there's a 10 and 11, and it gets diminishing smaller at 9, 12, then 8 and 13. In fact, they're mirrored to each other. This is almost a perfect bell curve right here. There may be infinite combinations, but the group of number combinations, they're more concentrated within certain areas. And this is how we get normal distribution of the bell curve. Because there may be many combinations, but at the summary of total, there's only so many of each type. This is how we come up with the central limit theorem, which we'll be using the rest of the semester. If you have a population with a mean, which is mu, remember, that's what that cursive U is, and standard deviation sigma, that's a small sigma, by the way, and take sufficiently large random samples from the population with replacement, then the distribution will be called a normal distribution. This is also called a Gaussian distribution after Carl Friedrich Gauss. He was a German mathematician in the 1700s. Now, we're going to be using these specific percentages. We talked about this before with the empirical rule. When we have a normal distribution and we determine our standard deviation from -1 deviation to the mean is 34.13%. And then from the mean to +1 deviation, 30.13%. So from -1 deviation to 1 plus +1 deviation, 68.26%. Or 68% of all the data normal distribution falls between minus and +1 deviation. From -2 to +2 deviations, 95%, 95.44. So if we have 1,000 bits of data, 954 out of 1,000, if it's normally distributed, should fall between -2 and +2 deviations. And then 99.73% should fall between -3 deviations and +3 deviations. In other words, if I had 1,000 unique points of data and it was normally distributed, 997 out of 1,000 would be concentrated between -3 and +3 deviations. Now, let's make sure we're reading the normal distribution properly. Which has a greater mean, curve A or curve B? Well, the mean is the average. And there's a greater mean on A. It's farther over to the right. The mean on 15, which we said the mean equals the median equals the mode in a normal distribution. You can see here, A has a mean of 15. B has a mean of 12. So it has the greater mean is curve A. Now, deviation is the spread. A greater deviation, a greater spread is in B. If you look at the deviation, if we look at 99%, it falls between 12 and 18. So that's about a range of about 6. Now, if you look at deviation of B, it goes to from 3 to 21. So there is a greater deviation there. Now, let's do some basic computations for deviation and normal distribution. And let's suppose I've collected some data here. The mean for pizza delivery is 30 minutes. It could be like Domino's or Little Caesars, 30 minutes or less. And the standard deviation is 5 minutes. In other words, from -1 to +1 deviation, that's what these dotted lines have developed are. 68% fall between 25 minutes and 35 minutes of all the deliveries. 95% fall between 20 minutes and 40 minutes. And 99.7% fall between 50 minutes and 45 minutes. So the normal distribution, we usually have a mean of 0 and standard deviation of 1. That is the standard normal distribution. And what this really means is we're going to calculate the z-score. We want to know how many deviations something is compared to a given mean standard deviation. And z is equal to the value you're looking at minus the mean divided by standard deviation. Again, you see your cursive u, which is the mu, divided by the little sigma. And this is how we determine how many deviations it is. Now, basically, when we talk about 3 deviations as 99.7%, if we go from negative 3.49 deviations to plus 3.49 deviations, that's basically 100%. That's all the area under the curve. Let's talk about some common z-scores here. And we're talking about volumes under the curve. A z-score of +1 would mean from the very beginning to the halfway mark, which is 50%. 50% of the curve is on the left, 50% of the curve is on the right. So, and then one deviation, I've written it down, is 34%. So a score of 1.0, a z-score of 1.0 would be 50% plus 34%, or 84%. A z-score minus 1, remember half the curve is 50%. And if I look at 50% minus 1 deviation, which would be minus 34%, that would be 16%. Now, if I'm given a z-score, I can determine what percentage is under the curve. And we use a thing called the z-score table. It actually goes from negative 3.5 to plus 3.5. And that's minus 3.5 deviations all the way to plus 3.5 deviations. Basically covers 100% of the curve. I've got a copy of it here. And if my z-score is positive, I know that's at least 50%, because a z-score of 0 is from 0 to 50% of the curve, right down the middle. So if you look at this little table to the left here, z at 0.0 is 0.5. And the way we read this is on top of here, on this part, where I'm circling the z, going down here are the tenths. Over across here are the hundredths. So what I'm going to do here is I want to look at 1.15. What percentage is under the curve? So I'm going to go, here's 1.1. And then I go across 1.10, 1.11. You see the 0.01 there, 1.12, 1.13, 1.14, 1.15, and that is 0.8749, which is what this is right here. In other words, a z-score of 1.15 is equal to 87.49% of the curve. Here's another example. I want to know a z-score negative 0.24. Now in this case, this is less than 50%. It's negative. A z-score of 0 is 50%, remember. A z-score that's less than 50%, that's negative is less than 50% of the curve, because 50% of the curve is down in the middle. We're going to say the same thing we did before. I've got the table from negative 3.4 deviations to 0 deviations. And what we're going to do here is I want to know negative 0.24. So I'm going to look up, same as I did before, what is negative 0.24? And right here is negative 0.2, excuse me. And this is 2.0, negative 2.1, negative 2.2, negative 2.3, and negative 2.4. So negative 0.24 deviations is 40.52% under the curve. So we look at deviations as across the horizontal line, but the space under the curve is what the table tells us it is. Now in this final example, we're going to use both sets of curves. Not difficult, but it is a two-step process. And I want to know the z-score that falls between negative 1.5 and z is 1.25. What space is under the curve? I'm going to look at 1.25 first. When I look at 1.25, I go to it's greater than 50%, so it goes from 0 to 3.4. And I'm going to go to 1.25, let's write it out here. I got to find 1.2 first. Here's 1.2, and then 1.2, 1, 2, 3, 4, 5. There's 1.25, 0.8944. So I'm going to put 0.894. I write terribly here, and I apologize for that. 4. And that is what I got right here for this first curve. Now the second one is looking for z at negative 1.5. And if I look at z at negative 1.5, this is the same as 1.50. Here's negative 1.5. And it's not 1.51, negative 1.52, it's 1.50. And there it is right there, 0.668. This is 0.0, z at negative 1.5 decimal point there equals 0.0668. Again, and I actually have the numbers typed up right here. So I need to find the space between these two. Well, this second one is the space in the very beginning to 1.25. Here's the space in the very beginning to negative 1.5. I said 1.5. The very first one was 0 to 1.25. Second one, 0 to negative 1.5. I'm just going to subtract the two. I'm going to subtract this one from here. And what I'm left with is this area right here. And 0.8944 minus 0.668 equals 0.8276, or 82.7% of the area under the curve.